It's high school.
I wish I could hold it with
No, that's not my waitressing job.
Good morning, everybody. I believe you have received some emails from Kyla. She's gonna come here at the end of the class. So if you have any questions or if you have any concern, you can see her. And also, you can ask me assistant. All right? Did everyone get the schedule? If you have any conflict, you can talk with me, okay? All right. Yeah, so let's take that. Right, it's September. Can you believe that? September. So are you good with the homework problems? Any questions from the homework? No? Can we move on to multiplication today? I don't know why he keeps doing this. Look at the sign that don't turn off the computer and still keeps turning it off. Okay, yeah. So we are on the third section, which is multiplication of whole numbers, 3.4, but we skipped 3.1. So it's our fourth, our third, right? So let's talk about the multiplication. If you think about multiplication, we can always extend what we did in the addition, right? If I extend what we did in the addition to multiplication, what can you think about the relationship between addition and multiplication? How are they related? Have you ever thought about that? How are multiplication and addition related? So when you're teaching multiplication, what do you do first? Or what would you do first? How would you introduce multiplication to your students who have never learned about multiplication? Okay, no addition and subtraction. We want to use them, right? So think about it. How would you do that? For example, let's think about 3 times 2. When do we do 3 times 2? 3 plus 3. When there are 2 3s. Yeah. So it's called repeated addition, right? So we can see the connection there. Okay, very good. So the first model that we're going to talk about is repeated addition models. For example, we write 8 plus 8 plus 8 as 3 times 8, because there are 3 groups of 8. 1 times 8 is 3 times 8. Okay. Well, later we're going to talk about the property like commutative property. Or not? Not?
That's fine.
Okay. Later we're going to talk about the commutative property. So 3 times 8 is the same as 8 times 3. We read this 8 plus 8 plus 8 as 3 groups of 8, right? So it's going to be 3 times 8. Okay, so the number of that 8, whatever that 8 is, like if we have 8 apples, 8 red apples, 8 green apples, 8 yellow apples, how many apples are there together? We are not looking at the distinction about the color, but we're looking at just the apples. So we can say there are 24 apples, right? That's the same as I just, put 8 groups of 3 apples, no matter what the color is. it's gonna be the same number. We're not gonna change the number of apples, 24 apples. We're just gonna group them differently. Okay? So that we'll talk about later. 3 and 8 here. When we are doing multiplication, 3 times 8, each of these 3 and 8 are called factors, right? If we do addition like 8 plus 8 plus 8, what do we call these 8? In addition, the addends, right? In multiplication, we call these numbers that are multiplied together as factors. How about the result of that? We call that product, right? In addition, what's the result of the addition? Sum. How about in subtraction? What was the result of the subtraction? The difference, okay? And in subtraction, you need to be careful about what language you're using there. The number that is subtracted is called subtrahend. The number you are taking away is called minuend. We are differentiating those two because a minus 3 is different from 3 minus 8. But in addition, a plus 4 is same as 4 plus 8. So we just call both of them as added. Similarly, in multiplication, we call 3 and 8, both of them, in 3 times 8 factors because 3 times 8 is same as 8 times 3. We just call them factors. We don't do like multiplication. Some people do, but I don't. And you don't have to. Okay? Alright. So if we use the number line model, we can only do the whole numbers. We're still on the whole numbers. So let's just do numbers from 0. If we do 8 times 3 or 3 times 8, what we can do is, using the number line model, we can show the repeated addition here, right? So we can go from 0 to 8, and we add another 8 there. Oh, this is not enough. Let's do that again. From 0 to 8, plus another 8, plus another 8, and I land on 24. So we can say that this is 8 plus 8 plus 8, but it's the same as 3 groups of 8. So 3 times 8 equals 24. You can do that, right? So that's how you use the number line. Okay, repeated addition. And another thing we do a lot is equal groups, right? I think this is actually more familiar to us, don't you think? Yeah, you do. So we have 3 groups here, and in each group you have exactly same number of axes. I have 4 axes in this group, second group 4 axes, the third group I still have 4 axes. This is still repeated addition if you think about this as 4 plus 4 plus 4. So if we are looking at the equal groups, in each group we have same number of items. We can do 3 groups times 4 items. And we get 12. What's the unit for the product here? What's the unit here? The groups or the items? 12 items, 12 axes for this case, right? Okay, so we have 3 groups. Pay attention to the unit that I'm using here. 3 groups. I have 3 groups of axes. 3 groups. In each group, I have 4 axes. The total number of axes are 12. Right? Okay, so when you are using the units, be careful about that. The multiplication is about coordinating numbers and sizes of the groups. Like what groups? How many groups? I have 3 groups of how many objects in each. I have 4 objects in each. So total is also an object. Okay? So be careful about the units. Any questions for this so far? I don't think so. So here are some examples of cookies. I really wish to bring some cookies, but I didn't have any time to bake them. Sorry about that. Maybe next time. So oopsie. Here I have 3 plates of cookies. And in these blanks in with my example of cookies here. Can anybody state this? Hannah? How many groups? Three groups. 1, 2, 3 groups of what? 5 what? 5 cookies. So 3 groups of 5 cookies equals what? 15 what? Cookies. Okay? Very good. All right. So I don't think you have any questions with that. And another new model that we can introduce to your students for multiplication is array model. This is kind of very famous model too. Okay? So we are making, rectangular array because it really helps us to look at how many in each row or how many in each column. We can make them as equal groups easily. We can see with this example, I have 1 row, 2 rows, 3 rows, right? Instead of groups, I can write that as rows. I have 3 rows, and in each row, I have exactly the same number. In this case, I have 4 axes. Virtual 4 axes, regular 4 axes, they're the same. So I can say 3 rows of 4 axes make 12 what? 12 axes. Okay, so that is the array model. When we are counting big numbers, I think it's so much easier for us to look at the total number when we are putting them in arrays, right? Okay, so that's what we do. And here's another example, and I'm asking you how many pins are shown in this example. This is bird's eye view, so you can just see circles instead of the cylinder shape. Okay, this is nicely organized. If it's scattered like that, it's gonna be very hard for us to count. Maybe just little kids do 1, 2, 3, 4, 5, 6. They are counting that way. So if we arrange that really nicely like this rectangular array model, you can count the rows or columns, right? If we count this by rows, how do we count? How many rows? 4 rows, and in each row, how many? 6 pins. So the total is 4 times 6, 24. If we count them by columns, I actually have them here. The rows or columns. If you look at the columns, we can see that there are 1, 2, 3, 4, 5, 6 columns, and in each column there are 4. So you can have 6 times 4 equals 24. Did we change any numbers there? No, we still have exactly the same number of pens, just like above. But the counting, how we count, how we group them is just different, right? Here we made 4 groups. Here we made 6 groups, right? Okay. I didn't see Rachel came in, so I don't think I actually shared the screen. Okay, is it better? Okay, so that then. Oh, that's not good. Anyways, another good model that I want to talk about is area model. This is my favorite. I don't know how many of you are familiar with this. How many of you are familiar with the area model? Yeah. This is not very well known for elementary, but this is heavily used for middle school and high school because you can use this for multi-digit and for algebra too. Okay, so let's take a look at some area model using the manipulatives. Okay, so looking at this, it's similar to array model, isn't it? So we can look at 3 in this column, 3 in each column, but there are 4 columns, so we can do 4 times 3. Or if we look at, horizontally, you can see there are 3 rows, and in each row is 4 items, 4 small squares, so 3 times 4. So we can see that. And I will show you some area model virtual manipulatives here because I want to show you how we can extend the area model here. So again, for the previous one here, you can see, oh, the area of this rectangle is length times width, right? So 3 times 4. And there are total 12 squares. That's area model, isn't it? You can always extend that to bigger digits. So for example, if you're looking at this partial product, for smaller digits, you can take a look at 5 times 5 that way, or you can decompose 5 into, let's say, 3 and 2. Because let's suppose your students didn't learn 5 times yet, but they learned 2 times and 3 times. So they know 3 times 5 is 15, and they know 2 times 5 is 10. So 5 times 5 together, it is 2 times 5 plus 2 times 5. Okay, so they learn, I mean, you can also teach them distributive property there too. If I extend this to bigger digit, so let's go with 216 times 25, for example. Make this too big. Okay, then 21 times 25. So this is 21 times 25. It's hard to count, isn't it? So what we can do is, we can decompose these numbers. For example, I can change this to 20 and 5. No, this is 21, so 20 and 1, right? And this one as 20 and 25, and 20 and 5, like that. So I made 4 different partial products there. So this big square is 20 by 20. It's easier for us to calculate, which is 400. So I can do 400 plus this part, 5 times 20, and 20 times 5, 100. And this one, 1 times 20, which is 20, and the last part, 5 times 1. So you add all of those partial products together to get the total area of this rectangle. That is rectangular method or area method. Are you following me? So it's really useful when you have bigger digits. Okay? When you are doing algebra, it's the same thing. If you change this to x plus 5 times x plus 1, you can just show that, and this partial product is going to be x squared. This is going to be 5 times x. It's going to be x times 1. This is 1 times 5. So the sum of them is the binary product. Okay? We're going to talk about that later too. So yeah, area model is very good model. So here's area model of 73 times 64. 73 times 64. I want you to represent this on your notebook by breaking 73 into 70 and 3, 64 into 60 and 4. These can be flipped over, it doesn't matter. And we're gonna compare that with the standard algorithm that we already know. Okay? Okay, so on your notebook, show 73 times 64 using that area model. And I'm gonna cover that up. You just need to have a problem. 73 times 64. I just wanna make you practice this. It's very useful model. So everybody on your notebook.
So do you want us to like actually draw out
Yes.
all of it?
Yes. 73 times 64. And when you are doing the area model, and after doing the area model, think about other models that we talked about, like repeated addition model, equal groups model. Think about that. It's not going to be easy to do that because we are looking numbers. But you will figure out, oh, that's why we're doing area model. I will give you about 30 seconds. then compare your area model with your neighbors. If they are similar. Okay, so what we can do here is, this is only one way of making area model with these numbers. It's not the only way. 73, you can break this into tens and ones, like 70 and 3. And you can also do 64 as 60 and 4. You can make 4 partial groups. Right? And here we have 70 here and 3 here. And we have 60 here and 4 here. And let's look at this rectangle. The area of this rectangle is what? 60 times 70, which is 4,200. 4,200. How about this one? 3 times 60, isn't it? So it's gonna be, what is it?
180.
180. How about this one? 70 times 4. 180. How about this one? 3 times 4. 4. So we got partial products there, so we can add them all together. 4,200 plus 280 plus 180 plus 12. And you get the answer for that. Now, how will this extend this to standard algorithm? Because we need to come to this. Anyways, algorithm. So when we are multiplying 73 by 64, what do we do first? We multiply the ones first, right? So 3 times 4, which is, well, I'm going to show the partial product here too. So 3 times 4 together, I just connected it, it's now 1. So let me raise it actually. So 3 times 4 is 12. And this is not 7, but it is 70, isn't it? So 70 times 4 is 70 times 4, 280. If it's 7 times 4, it's 28, but we have 70 times 4, which is 280. There are some teachers who are saying, what, 7 times 4, and put 28 and put 0 there without any explanation. That doesn't help your kids at all. Okay, so make sure this 7 represents 70, not 7. Okay, how about next? We are done with the times 4. How about times 60? Now we are doing 60. 60 times 3, 18, 10, 180, right? If you just do 3 times 6, it's 18, but you have 60 times 3. So it is 180. That's why you have the 0 there. Okay, because we are counting how many tens. When you have 6 tens times 3, it's 18 tens. Okay, how about this? 70 times 60. 70 times 60 is what? 4,200. So we can have 2 zeros because we have 7 tens and 6 tens. When you're multiplying them together, you have 4,200. And then you can add them together. 2, 6, and 4, 4,682. So let's compare what we have in this area model and standard algorithm. I'm pretty sure you might have already found all the partial products there, right? So we have 4,200 here, and we have 4,200 here. We have 280 here, we have 280 here. We have 180 here, 180 here. We have 12 here and 12 here. So all of these partial products in my area model are given in the partial product there. You can have some connections there. Okay, right. So area model is very useful for people visits. Okay. Another model is a Cartesian product model, or another word, ordered pair. We are more familiar with ordered are made from a piece of bread and a piece of cheese. There are 3 types of bread: white, wheat, and rye. And there are 4 types of cheese to choose from: cheddar, provolone, Swiss, and American. How many types of cheese sandwiches can the restaurant make with this choice? When they have 3 types of bread and 4 types of cheese. We can make the chart like this, or you can use the tree diagram. So when we are looking at this chart, we can see, what if I have only white bread? I have 4 different choices for the cheese: cheddar, provolone, Swiss, American. So you can read this easily, right? If I have wheat bread, I can still have cheddar, provolone, Swiss, American. These are all different from the first row. If I have rye bread, I can still have cheddar, provolone, Swiss, American. None of these are overlapping because we did it systematically. So this is one way. Or you can use a tree diagram. So if I use a tree diagram using the same information, we can start from 3 bread. So we have wheat bread, white bread, and rye bread. Rye is my husband's favorite. I don't know why. Anyways, if you have wheat bread, you still can have 4 different types of cheese, right? Cheddar, C, provolone, Swiss, or American. Right? Even if you have white bread, you can still have 4 different types of cheese: cheddar, provolone, Swiss, or American. Same for rye. Cheddar, provolone, Swiss, American. So there are no other options, right? Okay, so we can put that as Cartesian product model, putting wheat with cheddar, wheat with provolone. So I can actually write it next to it. Maybe like that. Wheat with cheddar, wheat bread with provolone, wheat bread with Swiss cheese, wheat bread with American. Okay, so we can count how many combinations there are. 3 times 4, because for each bread, how many options do we have? 4 options equally. So there are 3 groups here, and in each group you have 4 options. So how many ways to make the sandwiches? 3 times 4 many ways. Okay. So that's another thing. So maybe you have seen this kind of problem, like how many ways can I choose my outfit when I have 4 t-shirts and 5 pants, something like that. Okay, so you have done that a lot. For this kind of a question, can I only have ordered a pair like between 2 numbers, or I can have more? You can also have more. So for sandwiches, I can add vegetable there. If I have only lettuce and tomatoes and putting only 1 vegetable there, I can extend this to 2 vegetables. So I can have 3 times 4 times 2. Does it make sense? Yeah, so you can always extend the notion. Okay. Any questions so far? I think we are good. So yeah, here is the tree diagram, and there's organized list, and that shows 3 groups and 4 pairs in each group. So it's going to be multiplication, right? All right, now let's talk about the properties. Our favorite, isn't it? So before I show you anything here, let me ask you about your understanding about the properties. Okay, so in addition, we talked about the properties, right? Phone number addition. What property did we talk about? What property did we talk about? Closer. We are still on phone number, okay? So phone number addition. We talked about closer. What else? And combinatorial property. What else? Associative. then identity property. You can also think about inverse there too, right? Okay. Inverse property didn't work though because we had only a whole number, but it will work for integers because we're gonna do that negative number. Inverse doesn't work for whole number because we only have positive numbers. Okay? So now, your whole number, let's think about multiplication. We also have learned that these don't work for subtraction because it's not closed. Let's consider closer. Now I'm erasing this. Now we are in multiplication. Closer. So what is closer property? What is closer property? How do you check? If you don't remember, check your notebook. Look at your notebook. What did we talk about closer in addition?
So isn't that where you add the two whole numbers together and it equals a unique whole number?
There we go. There we go. So you pick two numbers, pick two or more, it doesn't matter, from the whole number. So that number you picked is from whole number and another number is from whole number too. Then the product, because we're doing multiplication, a times b has to be also a whole number. That is closer. Do you think that works for multiplication? You pick any two numbers from whole numbers.
2 and 7.
2 and 7. 2 is a whole number, 7 is a whole number. Product? 14 is a whole number. It is a whole number. If you keep doing that, is there any exception, any counter example that doesn't work for whole number? No. Every whole number, if you have any two whole numbers, multiply them together, the product is always a whole number. So closer works for multiplication. Awesome. How about commutative property? Same thing, if we pick two numbers from the whole number, we can commute them. Oh, now we are multiplication. So A times B equals, commute them. What do we get? Got it? B times A. Are they equal? Yes, they are equal. 2 times 4 is equal to 4 times 2. That's commutable property. Nice. Associative property. Diana?
So if you put, should we do the 3 numbers
Mm-hmm.
or 3 letters again? So in parentheses, put A and B, A times B, and then times C is equal to A times parentheses B times C.
There we go. Very good. So you have three numbers, three factors that multiply together, A times B times C. Did I change the order? I didn't, right? It's still A, B, C, still A, B, C. But how I associate them has changed. I can associate A and B first, so A times B first, then multiply the product of AB by C is the same as you multiply BC first, then multiply it by A. For example, if we have 5 times, let's say, 3 times 2 times 5. In order to multiply 3 by 2 by 5, 3 times 2 times 5, well, if we just multiply these together, you need to do that in order. So you're gonna do 2 times 3, 3 times 2 first, 6 times 5, then you get 30. But for me, I see 2 times 5 first. So I can do 2 times 5 before multiplied by 3. So I get 10, then multiply 3 by 10, so I get 30. It is still the same product, right? So here again, I didn't change the order. I didn't commute any number. 3, 2, 5, 3, 2, 5. It's the same order. I just changed the association there. Like whether you did do this operation first or the latter one first. Okay, so that's associative property. How about identity property? Lindsay?
Representation would be like, anything times one.
Yeah, exactly. That's yourself, right? The identity, you need to get yourself. So we pick any number from whole number, multiply that by 1, then you get yourself. Same as 1 times age, right? So in addition, we added by 0 to get itself, right? In a multiplication, we need to multiply by 1. Okay, so that is identity property. Inverse property for the whole number in multiplication doesn't also work because, for example, 2 times 1/2 is 1, so we know that 1/2 is inverse of 2, but 1/2 is not the whole number, right? So when we talk about the rational number, we would say, yeah, inverse works. But for whole number, inverse property doesn't work because it's not in the whole number, not close to the whole number. Okay? So these are the properties that we can talk about in multiplication whole number. Do we have anything else? Oh, we have one more. So that big fat zero, our favorite, right? So it's very powerful because whenever you multiply by 0, you get 0. Somebody talked about love is like multiplying by 0. I forgot about that whole sentence. Does anybody know? I'll find it out. Okay, I forgot about it. Multiply your love, multiply by 0 and 0. Okay, so if we use the manipulative or representation, commutative property, 3 times 5 is same as 5 times 3. You can just flip the rectangle over and show. This is 3 times 5, same as 5 times 3. Just flipping, the amount of the squares didn't change. Right? The same number of the rectangle there. Okay, associative property, because we have 3 numbers, it becomes 3D. So we have 5 in there now. And you can count, 5 times 4 in each flat. So we have 3 stacks of them, so 3 flats. So 5 times 4, you multiply that first. You see that in the parentheses, you multiply that first, and then multiply that by 1 to 3. But that's same as we're breaking up this way. We have 3 times 5. 3 times 5. So you are breaking the same rectangle just differently. Okay? So if you break it this way, you have that rectangle. How many of them? 1, 2, 3. It's still the same number. It still shows this big rectangle. This is how you break it becomes different. For this one, you broke horizontally. For this one, you broke vertically like that. Are you following? Okay. Okay, so one more property that we need to talk about is distributive property. This is heavily used, and you can always use this for algebra too. So we can do this over addition or over subtraction, right? So just make sure you distribute that multiplying factor to each of the term in addition or subtraction. How about going backwards? If you are given AB plus AC, and you say that's same as factoring A out, so A times in the parentheses B plus C, what kind of property is that? It's still distributive property, just backwards, okay? So what I mean here by is this. So if you are given 3 times 5 plus 9, that's same as 3 times 5 plus 3 times 9, right? So if I do, let's say I don't have that, and you are given only this one, and I see that, oh, I see 3 times here in that term, and I see 3 times on the second term, so I can factor 3 out. Because it's the same as 3 times 5 plus 9. It's hidden here, but it's exactly the same thing. It's still distributive property. Okay? So either way, either direction, you can say that's distributive property. Right? Okay. So it shows that So what kind of model is this? Area model. Area model shows the distributive property really nicely because I have 5 times. I'm breaking this into 3 and 4 instead of 7. So we can do 5 times 7, but let's suppose your student didn't learn about times 7. So we can, make the 7, decomposing that as 3 and 4 with a smaller number. Then you can show 5 times 3 plus 5 times 4. The same as 5 times 7. That is distributive property. Right? So 5 times 3 is shown here, 5 times 4 is shown here. Okay? Alright. But subtraction is the same thing. Okay, we can just distribute that. Okay, area model. So we know this. You wanna try this one? You can draw your own area model for 25 times 15. Okay, so use the area model, you know how to draw the rectangle and break them into whatever you like. And then show the distributive property with the same number. 25 times 15. Do that on your notebook, everybody. Times 15. One area model. 2 distributive. Maybe your rectangle decomposing could be different from your neighbors. I want to have a Sloan's idea. Sloan, how would you break this? 25. You can do it 20 times 5. 20 plus 5? Oh, yeah. 20 plus 5 is 25. So we broke 25 into 20 and 5. How about 15?
10 and 5.
10 and 5. Okay. If a lot of you did this way, you don't always have to do it this way. You can also break this into 10, 10 and 5. Whatever easy number you think it is. Okay, it doesn't matter. So if we do it this way, let's follow up with a Sloan's idea. What's the area here? 20 times 10, which is 20 times 10, 200. Okay, how about here? 10 times 5, 50. How about here? 5 times 20. If it's 5 times 2, it's gonna be 10, but we have that's 10th place, so put another 0, 100. 5 times 5, 25. So the final product should be 200 plus 100 plus 50 plus 25. So what is it? 375? So you can do it that way. How about using distributive property? If we do the same thing, what we did here is 25 times 15 is same as 20 plus 5 times 10 plus 5, right? So let's use the distributive property. So you need to distribute both 20 and 5, right? So you can do 20 and 10, and 20 and 5, 20 times 5. So we are done with distributing 20, and then we have still have 5, so distribute 5 to 10, 5 times 10, and distribute 5 to 5, and you get 5 times 5. That's exactly the same as what we have in the partial product there. So the total should be 375. So we can see the comparison there too. Okay, I will pause here. Let me see how much we have done. Because Kyla's here and we need to talk about it. Yeah, so we will continue that explanation when we come back on Friday.
Hi everyone. back here, yesterday you should have received an email telling you what school you were placed at for your after-school program clinical experience. I have some physical copies of your schedule and school information for your records, so I'd like everyone to take